So threading in Java. Multithreading in Java is complex. Why? Well, let's find out. You have your operating system traditionally with native executables. And operating system acts as a conduit between the hardware and the processes that run on it. It's usually a safe execution environment, right? Now, when multithreading happens with native applications, and I'm sure you already know what native apps are, when basically the machine code is organized to the local hardware architecture. So program like Word or Excel is native because the binary version of the code is understood directly by the hardware architecture, the local assembly language and the machine language, right? So when any kind of management needs to be done, it is handled by the operating system. So when you have Java applications or applets, those go through the Java virtual machine. The Java virtual machine is an operating system-like construct. So we have now got two operating system, an operating system running on top of another operating system, which makes life complex. Because when you end up creating a thread in Java, it's handed to the JVM, and JVM can have excuse me, need to enable editing in this so I can draw on it. Sorry about that. So when threads are created or anything is done in a Java app, it has to go to JVM, and JVM has to either decide to hand it to the OS or handle it itself. When Java virtual machine runs on an operating system, it's always handing over the control to the operating system it's running on. So if anything is created here, right, it will be run by the operating system. So there is this thing called the scheduler inside the operating system. Scheduler inside the operating system is the one that is taking a process and handing it to the CPU, right? So there are a ton of constructs that will play a role in our head as we begin to think about multithreading, guys. And I want you guys to please think about these. So scheduler is allocating units of time on a processor, and that's usually the responsibility of the operating system, right? There is a scheduler inside the operating system, inside the Java virtual machine too. Sorry, please forgive my writing here with that little pen because it's worse than kindergarten, I know, but nothing I can do. So there's a scheduler in the JVM, there's a scheduler in the operating system. Scheduler in the JVM is turned off. You can't have two cooks in the kitchen. So what happens is that when there is a thread, the thread is handed off to the operating system, and operating system takes care of basically multi-threading at that. I mean, basically it takes scheduler here takes care of managing all the processes and threads with it. Okay. So now the thing about the Java virtual machine is that when you try to start a task, you're at the mercy of this operating system. So generally, a process will have many tasks, and each one of those tasks will be registered with the operating system. So there is this thing called system thread group. I just drew. System thread group is this interface that every time you create a new task, it's going to tell the operating system about it. We'll pass a reference of that so the scheduler has it, right? And I started my talk by saying threading is complex for these reasons. Okay. So first is which scheduler. Second is system thread group and handing off the task, right? So you always are going through an intermediary. It's like a staff member is reporting to a manager who's reporting to a director. And when you have that extra layer of management, it will slow things down because the communication has to be sent through the manager. Even though the manager here is handing off some tasks, some of its responsibilities to the director, the operating system, right? So that's just at a high level. But now let's look at processing context, process context actually. I think we all know what a process is composed of, right? It has a state. It has memory. And it has a program counter that tells us which instruction is active. When we talk about memory, we have code segment, data segment, stack, and heap. And all of these things, program counter and memory, right, kind of describe the state of a process or its context. Make sense? So the scheduler in the bottom has scheduling algorithms. Scheduling a thread. So those could be, it could either be round robin or it could be priority based. As a Java developer, you don't really care about knowing these in detail, but you should have a sense of what it is, and you may already. So priority based is every thread or a process has a priority attached to it. And when a thread is scheduled, under priority based, the highest priority thread gets the attention, and the lowest priority thread in a busy environment will start. Does that make sense? Just like in class, if I said, okay, certain people have higher priority on questions. So it's likely that if in the execution time, the folks with high priority end up asking all the questions, the ones with low priority will be end of class, right? So that is referred to as thread starvation. But we could also have a more communal type scheduling algorithm, which is round robin. a fixed amount of time is allocated to each thread or a task. So the operating system might say that I'll give a unit of time in which you can execute 200 instructions. And after that, you have to relinquish control. And I want to give the control to the next process. And if there are multiple processes in running, everyone gets a unit of time, so everyone is making a little bit of progress. But in switching the context of one process to another becomes a time-consuming proposition because you have to archive the state of a process and bring it back, right? So there are performance consequences with round robin. And if I were to exemplify round robin to you guys in a minute here, I could say I have process 1 and say process 2. Just keep it simple. And we'll say that process 1 has 350 instructions, process 2 has 800. A unit of time or a quantum of time is 200. So I can process 200 instructions. Process 1 takes the first quantum, is done with 200, and it has 150 remaining. Process 2 gets the next quantum. Then I go back. I take out 6 quantum. I'm done. Process 2 is done. You see? Does that example make sense? So that's round robin. And it is modern operating system implement a hybrid of the two. Okay? I've covered some basics here, which you'll normally get in an operating systems course. I mentioned that in a nutshell, operating system is the conduit for managing everything. And the key thing we're worried about learning is the scheduler, which basically will schedule the tasks or processes. Tasks run inside a process. We can have native or non-native programs. Native programs are directly managed by the operating system. Non-native programs running with the Java virtual machine are managed through the Java virtual machine. We also said there is a scheduler in JVM and operating system. When running on the OS, JVM turns off its scheduler and uses the system thread group to hand over any of the task references that are created to the operating system. As a result, the control is all in the operating system level. Now, when you, from a Java thread, if you end up saying start, you are making a request, and that request is received by the scheduler. The scheduler, if it's busy, it's going to say, well, thank you for your request. And maybe it's serving something else. Maybe it's serving another thread in the native executable, and when that is done, then it says, okay, now you can start. So there is a callback, right? A request is made, and then the scheduler says, okay, I'm ready to go, and it sends a message back and says, okay, now you can start. That's the unreliability piece of Java's multithreading. Because when you say start is not guaranteed. When you push a button in the car, start, it should start. And it's not like, 30 seconds later. Because you want to hit the gas pedal and go. That's not the case with Java. Right? So there's that reliability quotient that you need to be aware of. So some basic things. Multitasking, the ability to do multiple things at the same time. We human objects multitask. We breathe, listen, and talk at the same time. Our heartbeat is running at the same time we're talking. So there is true multitasking. But then there are some things that on a computer system, the multitasking is a direct function of how many CPUs you have. If you just have the one, then you can only do one thing at a time, but you can have a show of doing multiple things at the same time. Meaning you have many processes running on your computer system with one working at a time. The nice thing today is that most of your even mobile devices have dual core processors, so you can be truly multitasking on two things at the same time. Then there are these terms, non-preemptive and preemptive. Non-preemptive refers to being selfish. Wait, what does that mean? Once the thread gets the attention of the CPU, it will not relinquish control until it's done. If it's using round robin, it's using the allocated block of time. Preemptive, if CPU has given attention to the process, it doesn't have to complete, because if a thread of another priority, higher priority comes along, it will yield to that. So the general idea with preemptive is creation of a safe execution environment for running threads and processes. Multithreading. We talked about the concept of context switching. Moving from one process to the next or one thread to the next. So threads generally live inside a process. And they are independent execution paths. We're talking about Java here specifically. So each thread will have its own code fragment, and it will execute, and then it will get garbage collected. There's no limit to the number of threads you can have per process. Threads can be either software controlled or can be native OS threads. Software controlled are generally non-preemptive, selfish. Threads controlled by the OS are preemptive. OS threads being preemptive, why? Because the operating system is supposed to be the safe execution environment, right? It's supposed to harness this environment where all processes can run so things don't crash. And most operating systems today are pretty good. We bring in this term called thread safety. The idea that JVM and packages are thread safe means that data corruption doesn't have to occur when multithreading is used with objects in Java. Because all Java threads are objects. And when you have a Java object, right, that's a pretty cool thing because you don't have direct memory access. You can only use the reference to access the object. You have no dynamic memory allocation. At least you can't touch the memory directly. There are no pointers. So that adds a lot to the safety of a thread. Okay? Threads are also re-entrant, which means you can carry on forward where you left off. Re-entrant. I'm going through context switching. I'm done with 100 units of work. I need to do another 300. I can just start with the next instruction. And I'll have my context back as needed. Context, of course, being native OS threads. There are also some third-party packages, but that's immaterial for this conversation. That's your running context. One, JVM can have multiple threads. Just always have a main thread. You'll also have a garbage collector, and then so even a simple hello world program has two threads. You have your JVM and your application. We already talked a little bit about this. Windows system uses time slicing. Other operating systems may not implement time slicing, but might implement priority wave. Most modern operating systems implement both. One important thing, Java runtime is preemptive, and high priority threads will grab the CPU. Preemptive is selfless, right? Non-preemptive is selfless. I like to use those terms because it drives the point, it drives the meaning home very quickly. So you're going to work with the java.lang.Thread library, and the thread class basically has these 4 states that are supported at a high level. Sorry, I'm having trouble drawing arrows there. Java also supports thread priority. Priorities is, although it doesn't have any value, because you can go in and tell, a thread can tell the scheduler that I am very important. But a priority has no meaning, because it may be treated differently, because there might be threads of higher priority from other processes that may take precedence. Java supports the concept of synchronization. You guys will be using this in your lab assignment. The idea of synchronization is that shared resources can get access to, or a resource can be shared between multiple threads and without causing data corruption. So, an example, so just to focus on the concept of synchronization. An account a deposit method, I'm going to deposit 50 bucks. So what happens is thread 1 reads the and now the balance is supposed to be 150. And at the same time, thread 2 comes around and gives a deposit of $100,000. Are starting to look really good. Thread 2 wakes up now, right? And it will go off and say, okay, the balance is 150. So the concept of synchronization in Java is that account object should be locked. Meaning if T1 is working on it and it got interrupted, other updates should not be allowed. That's the point. If T2 is doing an update, then T1 should not be allowed. So the right balance here would obviously be what? Now, if T1 wakes up, it should say, okay, I'm going to do an addition of 50 bucks, But let me start again. I'm not just going to take this thing. I'm going to start the process all over again, and I'll read the balance to be that. Then I'll add $50 to make the balance that. Synchronization is working. Implementation in Java is very easy. It's the underpinnings that become somewhat complicated, and we want to understand that very clearly. So maybe tonight is the concept night, and Wednesday would be the implementation. And there are a lot of concepts here. We also get explicit thread control in Java. When we say explicit thread control, you can make a thread wait. You can interrupt a thread. You can suspend a thread. You can resume a thread. You can sleep a thread. See, there are some things that are okay, but some things are not. Like wait is okay, sleep is okay, suspend, resume is not, or interrupt is not. Why? Because if you suspend or resume, those methods are not deprecated anyway. But if you interrupt a thread, if it's hanging on to shared resources, what will happen? You may have to restart the process completely, right? So wait and notify are the good ones. And those methods are inherited from java.lang.Thread. You all know that object class is a superclass of all class. So here is the thread lifecycle. You call the new method in the thread class. The thread is considered spawn because you just created an object. And then you say start. And then it's slave to the CPU for execution. Why? Because we have sent a message to the CPU and say, hey, I want to be scheduled. He comes back and says, okay, you can run now. And when the CPU comes back and says you can run, that's when you run. So from a running state, you can go to a block state. Block state means one of these three reasons. You go to sleep, meaning a thread goes to sleep, not you, excuse me. You yield to another thread of higher priority, or you wait, maybe for I/O or something. And then you can get out of the block state by using when the sleep is over. When you yield or wait, you basically notify. There is a fourth reason I want to mention, which is the scheduler in the operating system can act up, and it can say OS interrupt. What does that mean? You're in the middle of execution. And you're interrupted. So there is no remedy for that here because that's external to the process. And all you do is wait until you can resume, and then you resume. And that's just a function of the scheduler. And when you're done with the task, that the thread goes from running state to dead state. The dead state is simply when the run method is done. And if you wanted to stop a thread properly, you could set that thread object to null, and then it will be marked for garbage collection. Okay? As you can see, stop, suspend, and resume have been deprecated. So here is some code, some initial starting point. You can extend the thread or you can implement Runnable. In both cases, you write the run method, which is the body of the thread. It's main is to process as run is to thread. You get it? You write the main for the process, For a thread, you write code in the run method. The run is defined, and it's an empty method, and it has to be overridden. But the problem with the run method is also that it cannot be called directly. I'll explain. Like you see here. We have a class that extends thread. We have a run method, and we go in and write some instructions, quote unquote, do something. And in the main, we instantiate that object and call start. Notice we don't call run. We said w.start, which means what? Make a request to the scheduler to start, and then all that happens, which will invoke the run method automatically. Okay? Another example. 2 separate threads of type widget. This is another way of coding. They're not sharing widget. There are 2 separate threads of type widget. So each time you call start, each one will call its own run method. Okay? This will become common knowledge when you start doing your threading implementation. Here we are using the interface. When we use the interface, we need a thread object to link the interface to the run method. Does that make sense? We create an instance of widget, we create a thread, and since widget implements Runnable, I can pass that to the thread and call start. When I call start, it will end up calling this run method. Polymorphism. You may have to think a little bit about that. So we look at this example, right, of why synchronization will be helpful. So the way synchronization is done in Java is by using monitors. So there are these semaphore-like things or lock-like things that are implemented on resources. Anytime you say you want to declare something as a shared resource, inside the Java virtual machine, a monitor will be created to facilitate the sharing of the object. Now, what does this monitor do? It says, well, there can be many people or many threads waiting on sharing a resource. So the monitor will keep track of all that. Monitor will also keep track of which thread is currently locking the object, and when the thread relinquishes control, that is actively locking, it will notify all other threads that are waiting. And then whichever thread gets scheduled will continue running. We'll grab a lock and then. So the usage of the wait method, the notify and notify all, is prevalent with the usage of monitors. And when I show you the code implementation with some examples, you'll see this coming to life. One thread obtains exclusive access to an object only via the monitor. And you have to do some special things to enable that by using the synchronized keyword. So all these old methods, stop, suspend, resume, are gone because they cause stealth bugs. We should therefore never even use them. So then how do we operate? Well, we can, in the run method, add a condition that we periodically check to see perhaps if I'm alive. So there is a system call that you can make as a thread to an operating system, and you can say, am I actively running at this time, right? So there is a static method called thread.current_thread that basically returns yes or no, and you can use that as a condition. Using notify all, or wait is a good thing. Thread.interrupt, I'm not so sure. So here are those things illustrated. So, we create a thread, right? We start the thread in the start method. And if we were to stop by calling me.stop, it's a wrong thing to do. But this is a good thing. Like, so saying this thread equals thread.current_thread, and then saying while true in an infinite loop, so your run method is running forever. Instead of doing all of this, we replace this code with this. And we say me equals new thread with the current object and start. You probably need to just compare the two. So this is still the same, but look at the stop method. Please focus on that. We basically say me is equal to null. And then in the other part, we said this in two separate statements. We put that in one statement. When we say me equals thread.current_thread, am I the one that is actively running at this time? That's a static method that you can use for that reference. Non-thread safe state. What is non-thread safe state? I am using synchronization. I have a monitor. I've got exclusive lock on the account object, and I'm updating the balance. I'm suspended. Now, that information of the fact that an object has been logged by a thread is kept in the monitor, right, within the JVM. If a thread is suspended, no other object can access it if the thread is gone. That is opposite of thread safety. So we have all these methods that we like to use. Minus this. Priority. So there is an integer value that can be assigned to each thread, and I'm going to again show you some examples, and you'll see the reliability of priority. I've actually got one example where two threads start, and the one with the higher priority should get scheduled and should count more than the one with the lower priority. And what happens is the opposite. A thread of lower priority ends up counting to a higher value than the thread of higher priority. So a thread with a higher priority, in principle, gets scheduled ahead of those with lower. But there's no guarantee. This is another unreliable piece of Java's multithreading. And you can alter their thread priority by using the set priority method. So there is that little bit of explicit control. So something like that. So you can say, I've got T1 with normal plus 1, T2 with max, and T3 with whatever priority it currently, whatever priority T1 has plus 1. So T3 becomes a little bit higher than T1. Daemon thread. This is another thing on concept. Daemon thread is our background thread. Normal apps won't use these, but when you talk about Java's garbage collection, it uses a background thread. So Daemon threads generally use the CPU cycles when those CPU cycles are free. Unless you're running out of memory and the garbage collector then needs to do some work, it will then interrupt other threads and get to work. You can create a normal thread and call the set daemon method, and that will make any thread a daemon thread. What can you do in a background thread? Well, if there are some sort of I was going to use the word not so important activity, those can be done in daemon thread in the background. So for the JVM to exit, all active threads should be done. Daemon threads can still be around. We also got thread groups. This is used for grouping thread objects. If you want to say groups of threads, it does not mean that if a group of threads, are started, that they'll all start together or stop together. It just is a way of creating like an array and having polymorphism to start a group and stop. You just end up writing a little bit less code, that's all. So you can do the same thing by creating an array of threads and calling start on each, because you'll have objects of the same type, right? Or you can just create a thread group like you see here and include those threads in each group. So when you do end up using the syntax, you have the new thread associated with the thread group. So, meaning of thread is helpful too, because like in this case, what am I doing? I've got 10 threads, and when I instantiate the thread, I'm giving it a name. And then that's just a argument you pass to a thread, right? To the thread constructor, and it names it. And then you call getName to print out the name. So idea of synchronization. So you'll end up using this, like I stated in your lab assignment. I explained the concept of synchronization. The implementation is that you have this concept of a critical section. So the part where I'm going to update the balance, right? For the example I provided earlier, this one. If I were updating the balance, that would be the critical section. And what I want to do is, I want to grab the log for the shortest amount of time. I don't want to grab logs for long durations, but for the shortest amount of time. To avoid the said things on this slide, I don't want to cause deadlocks, and I don't want to cause starvation. You all understand what a deadlock is? The idea that two threads are waiting for each other to release what each thread wants. And there is this complicated dining philosopher's problem that you can Google and read. Every synchronization textbook has this on, like in the first chapter. So the idea of a deadlock is this. Resource X locks thread, there is thread A and thread B. Thread A locks X but wants Y. Thread B locks Y but wants X. You're in a deadlock. And to fix this, one of the resources has to get rid of X or Y. Right? This is a classic deadlock situation. And it's also a short intro to the dining philosopher's problem. And that is an interesting story about, a bunch of philosophers sitting in a circle, trying to eat their dinner, and they want you to use fork and knife, and they only have one off. They articulate it pretty nicely. Now, if that becomes too much, look at this picture. Is this pretty clear? I figured it would be. But dino philosopher issue is a computer science representation of a deadlock. And so in your computer science lifetime, you should look at it when you get a chance. But someone will ask you in an interview, and so it's a good idea to know it. Yet another concept on communication. You can implement what is called IPC, inter-process communication, or you can also implement inter-thread communication. So there are strings in Java that enable communication. So you can create threads that are either consumers or producers. In our example, a producer thread would be what? A thread that sets up the automotive object after reading a file. A consumer thread would be the one that uses that automotive instance to configure a car. And the communication between those two threads can be done through piped output stream and piped input stream. I promise you we will not end up implementing any of the inter-thread communications. But I wanted to have this on the slide just for your fun. Okay? So producers write to piped output streams and consumers read. We're going to do something better than this. We're going to write a server and client using socket. That'll totally make your life very interesting. So this is how producers and consumers work. You've got a piped output stream, a piped input stream, named as producer and consumer, and we call the connect method. Producer writes something, but consumer can read it. Okay? So this is all I have on concept.